Welcome back, Calcsters. I have been to the Nether a bunch of times. I've died in the Nether a bunch of times. I've died in the Nether around a mob of terrible animals that kill me, and I've respawned and not been close to my portal and gone back to the Nether to get my stuff and die, and then respawn and go back to the Nether and repeat until your heart is like totally stressed out and annoyed by the situation. And then I haven't played since then. So, I do have all my stuff back, just for the record. Okay, we just found a function that gives a value of every possible derivative for this position function. That is a huge time saver unless you want to compute infinitely many limits. When we're looking at this, our first main topic in 2.1 was tangent lines. Our second main topic, and this one's going to go pretty quick, is going to be on the derivative. And I know that we've already talked a little bit about it, but let's refine our kind of thinking on this. The derivative. Okay. Now, the slope that we've been finding, the slope of our tangent line, what's weird about it is there's several different interpretations. We can interpret this three different ways. So 3 interpretations. I'm going to make that a tilde. Interpretations. Okay. There are problems that, for me, I personally have always found them kind of challenging, but I think I'm at a point now, and I hope I'm at a point now, where whatever issues that I've had or seen people have, we can sort it out. Okay, the first one of these is we can think about it as a geometric interpretation. Now, the geometric, if you'd rather not think of it with geometry, you can simply think of the graphical interpretation as well. What this does is it tells us exactly what's going on with a function at some point in time. So if we want a graphical approach, let's just look at a quick one. Let's consider the function f of x equals x squared. Now, if I wanted to think about its derivative, rather than at a single point, just the general derivative, just like we found on part C just now to say find me the slope anywhere, I'm going to skip ahead a little bit, and some of you may know this shortcut, but I'm going to tell you its derivative is 2x. And you probably see that there's a pattern that you want to exist that does exist exactly like you want it to, just so you're aware. However, I don't want you to graph the black one. I'm going to draw my coordinate plane. I don't want you to graph the black one. I just want to graph the green one here in a second. Okay. Do you guys agree that this is roughly what x squared looks like? X squared. It's like that, right? And I'm going to try to make this a little bit nicer. Okay, there's x squared. Now I'm going to ask you a couple questions about it, and I would like to use the ruler, but I'm going to try to do it here. Could you imagine a tangent line right here? Is it this line? Can you tell me anything about the derivative at that point that I just plotted? You can't really give me a number, but you can tell me one thing about it. Say it again? It's positive. If I check here, is it still positive? Is it a little bit different, though? And I guess more specifically, it is different. What's different about it? It's steeper. Do you agree that with the idea of the derivative, it means that the rate of change here is bigger? So the farther in time or along the x-axis I go, does it keep getting steeper and steeper? Like up here, it'd be like this. What about as I get closer to this vertex? All of a sudden, my derivative starts getting, instead of steeper, we get a little bit less steep until it gets to what value? There's a point where it'd be 0, right? Now, it turns out that this whole idea can be represented pretty easily by this line. This is the graph of the derivative. Now, the derivative is 2x. We haven't found all these general rules yet, but let's see if this makes sense. At x equals 0, what did you say the slope would be of the tangent line of my parabola? What's the value of this green function at x equals 0? On the entire left side, if I were to draw any of my tangent lines over here, you can't give me numbers, but you can tell me about something about them. What are all these slopes? What's the value of my derivative over here? These are all negative. They link up with each other. We have a way, and we'll practice a lot with this, about how do we make sense about what's going on given the graph of a derivative. Okay, that is going to be a large focus in later sections. Another interpretation, rather than just thinking pure graph, is we can think about it as a rate of change. Now, for our rate of change, I don't want to talk a whole lot about it, but it's usually, we'll have units, right? It's associated typically with physics stuff, but it's not always. If we think of any situation where stuff changes, if I have a tank that has a hole in it, what happens to the water level inside? It starts to lower, right? Like it'll start to drain out. Do you think it drains faster at the beginning when there's more water pushing down than it will later in its cycle? Probably. The pressure's higher, right? It'll push out a little harder, so the rate of change of however fast that water's draining out will like vary. That is 100% a calculus problem. We will deal into this. I don't have a whole lot to say about those ones there. The last one is the tabular approach. Now, this language, we're going to sneak in a small little example here. Tabular is ugly, but it just means using a table. Now, sometimes we're going to be finding derivatives from a very specific function. That is what we did on example C today, last class. We found the value at a single point. However, I have a quick example here of the tabular one. And again, we'll dive into these more. But I want us to consider an example where we're heating some water. And this is a very realistic situation. If you guys want to do a little bit of chemistry type stuff, we can probably borrow the lab to go get our own data at some point to see these problems in work. If I asked you to heat up some water and take the temperature as time goes, could everybody do that? Like you could check the temperature, right? So let's look at one here real quick. I want to know a time t and what is the temperature of the water, and we'll say W of t. And we'll work in Celsius since we're in a science and math class. Okay, do you guys know how warm it is in here right now? Would you guess in Celsius? At time 0, we're starting right now. What do you think the temperature is in here? What is it in Fahrenheit, roughly? 90? Too high, too low? 40? Too high, too low? Okay, so we're between there. You guys, I think, have a, just guess. I don't care if you're right. I don't know what it actually is. 65 is probably pretty close. Fahrenheit, 65, but we're going to use Celsius. Let's say, I don't know, it's at 17. 68 is 20, so it's really not quite 17. Now, let's pretend that I put this on a hot plate. Okay, I have a hot plate. I don't physically have one, but we can pretend, I think. How long are we going to wait? What next time? Sure, at 1 minute, what do you think the temperature is going to be? Will water heat up in 1 minute? Maybe a little, 18 maybe? And then let's take another big step. Let's say we go 10 minutes later. Give me a number. 30. Okay, and then we'll go 10 more minutes, and if we increased that much, sorry, this would be at 20 then, I think that we would probably be getting closer. Let's say we're at 80 at this point. Guess for 30? Okay, don't write it. I want you to tell me why I don't want you to write it. Why not? I'm claiming after 30 minutes, my water that I'm heating is 120 degrees Celsius. Why didn't that work? It's too hot. What does water do at 100? It evaporates. Any extra energy doesn't increase the temperature of the water. Any extra energy that we add changes that liquid water into steam. We can't get above 100 if we're just boiling it unless we're taking the temperature of the steam. So let's say it's at 100 here. Which means at 40, if I wanted to put it, what would it be at still? 100. It could never go above that. However, here's what I want us to do. I want us to approximate W prime of, let's say, 5. When people are actually getting data in a lab setting, unless you have like the top of the line stuff that can take real measurements continuously, you're going to get gaps in time like this, right? Nobody can continuously write down and measure and look and do all that at the same time. Do you think there might be a function that we could use to predict the temperature at some point? Absolutely. First thing that I care about is if this is time and this is the water temperature at time t, what is W prime telling me? Talk with your neighbors, I'm going to give you like 30 seconds. Before you even think about estimating it, I want to know what would W prime even mean. Let's talk it out. Good answers, bad answers. I just want answers.
How the temperature changes at that point.
We're going to be a little bit more specific, but I like your idea. You said, Alex, you said.
One more word we needed there. So kind of, I would say how quickly the temperature's changing, right? That rate of change, I think.
All right. Yeah, absolutely. That's a weird way to word it, but I agree with you 100%. Okay. I like Alex's idea. I didn't check with that side of the room. Thoughts?
When the temperature changes.
So when the temperature changes, kind of. When, what do you mean by that? I think that you're probably on the right track. Avoiding eye contact, all right. This is W prime, right? Or sorry, this is W prime. And a derivative we just think of as a slope or a rate of change. W prime of 5 tells me at 5 minutes, at what rate is the temperature changing? So we might get, I don't know, we'll estimate here in a second, but there's a point in time where the water is increasing at 1 degree Celsius per minute. And I would estimate that to be that first minute, it would seem, just based on that. And then as water gets warmer, it gets easier to heat up, takes less energy to do that. Okay, so we're trying to approximate W prime of 5, or just say, at 5 minutes, how quickly is the temperature changing? Do we have that data point? Do I have 5 minutes ever? I didn't write it, but it's in there, isn't it? Is there an interval which 5 lives in? Like, it's between 1 and 10, right? Now, this is going to be a bad approximation because I have to base it off the real data, but I know that time 5 lives somewhere in here, between these 2 points. Now, we can't approximate a tangent line here, but when we looked all the way back at the very first derivative that we wrote, we took a secant line that became a tangent, right? So the best that we can do here is just the secant line then. So let's find it. All I'm really asking for here, we can't do the actual limit and do it analytically, but I just need to find the rate of change, or the average rate of change, between these values. What goes in my numerator? Is it W or time? Which one's the independent, which one's dependent? Does the temperature of the water dictate how much time has passed, or does how much time has passed determine the temperature? So that's, time is my independent, my X value, which means we better pick the temperature up here. 30 minus 18, and this, I'm gonna include my units, because we haven't written them anywhere. How do we measure temperature based on these numbers? That's degrees Celsius, over, what's the corresponding time? Minus? Good, and that's in what? Minutes. Okay, so if we wanted to just approximate a derivative based on a data table, which is exactly what we're doing, I think we can knock this out. What's 30 minus 18? 12 over 9. And that's degrees Celsius per minute. And let's clean this up one more. 12 over 9 is like 1.3, right? Is it 1.3? Yeah, 1.3 approximately degrees Celsius per minute. Every minute that goes by, we're estimating here because we have bad data, but every minute that goes by, the temperature is increasing by 1.3 degrees Celsius. What if I said hypothetically that it was what if it was negative? What would it mean? What? It's going down, meaning the water would be doing what? Not evaporating necessarily, just cooling down. Like if I set a cup of coffee here and we just measured the temperature throughout the day, you'll see I drink room temperature coffee 90% of the time. But doable? Okay, so yes, I said by 10 and here we are. I want you guys to work through some problems for practice. I'm going to write them on the class here. Okay, for today, we are in here. And let me see, I think that this is actually the end of the section. But I don't know why I called it, oh, there we go. Okay, homework 2.1 you will find on page 169. And it's going to seem like quite a few. And it is, but we got 25 minutes right now. I want you on page 169 to do problems 2, 3, 7, 11, 20, 23, 27, 33, 37, AP 2, 3, and 4. Okay, we have a bunch of time in class. Let's do it to it. I'm here to help as needed.